Let's talk about Henry's Law. Here I have a bottle of distilled white vinegar. It's useful for many things, cooking, making pickles, cleaning, but it does have a very strong smell. If I were to open this bottle of vinegar in a room, who would be able to smell it? How may you go about answering that question? Pause the video and write down some ideas. So here are some questions you might have come up with. What is vinegar? At what concentration in air does vinegar have a noticeable smell? And because you're in this class, what law in chemistry might govern vinegar in water as it's moving into the air? So let's break this down. But first, you should know that by the end of this video, you should be able to use Henry's Law to calculate equilibrium liquid or vapor concentrations, and you should be able to integrate the use of Henry's Law into our pre-existing problem-solving framework. So vinegar is acetic acid. In the formulation that you buy from the store, like this jug right here, vinegar is normally 5% acetic acid in water. Because water is odorless, we'll focus on the acetic acid. To find information on acetic acid, I'm going to go to PubChem, which is an online database with information on hundreds of chemicals. First, I can see the structure of acetic acid. You see the carbon here with 3 hydrogens. Here's the carboxylic acid group. For the sake of our question, I'm interested in some hazard data. Here you see the hazard classification, and if we scroll down, we'll see that the irritating concentration is 25 milligrams per cubic meter. We can also see that the low odor threshold is 2.5 milligrams per cubic meter. Thus, we can conclude that if you're in a room where the concentration of acetic acid in the air is increasing, you'll smell it before it becomes a bad problem. So first, let's determine the concentration of acetic acid in the headspace of the container. The headspace is the air above the liquid in the container. So you can see right here, this part is going to be the headspace. So we'll use Henry's Law to relate the aqueous concentration to the concentration in the vapor in the headspace. So Henry's Law assumes that the vapor and the liquid phase are in chemical equilibrium. Because our bottle of vinegar, I just went and grabbed it out of my kitchen, it's been closed for some time. That's a good assumption. So here I have a diagram of acetic acid, CH3COOH, in the water, or aqueous phase. And I have 2 arrows showing an equilibrium between the aqueous phase and where it is up in the gas phase. And this little symbol with the triangle and the 2 lines, that's very commonly used just to indicate like a water level. So what we need here is our Henry's Law constant. And basically that's just a ratio between the molar concentration in the aqueous phase and the partial pressure in the gas phase. So I've written this down here. We have our aqueous phase up on top, and we have our partial pressure on the bottom. So we can look up Henry's Law constants for many different compounds. But first, I want you to look at this relationship. So what does it mean if KH is higher or lower? So if it's higher, that indicates that it has more of a tendency for the aqueous phase. If it's lower, then the compound has a greater tendency for the vapor phase. Whenever you look up Henry's Law constants, be sure to note their units. Some sources will give you the inverse of the definition that I have here, but you'll catch that if you look at units. Some people also forget that the vapor phase concentration needs to be a partial pressure. You'll also avoid that mistake if you are paying attention to units. So when I look up the Henry's Law constant, or KH, for acetic acid in the table that I have, I see 2 numbers. 7.66 times 10 to the 2 moles per liter atmosphere, and 10 to the 2.884 moles per liter atmosphere. These are two ways of reporting the same number. You can check this with your calculator. When we look up the Henry's law, we see that we do need to convert our percent acetic acid, or here I just wrote that as HAC, to moles per liter. So I'll start with our percents. We've got 5 grams of acetic acid for every 100 mils of water. And then I can do some calculations, and I come up with a concentration of 0.83 molar. So now we can plug that into our Henry's law equation. So I'll rearrange and put the partial pressure of acetic acid over here on the left. And I can solve this equation, and I get 0.00109 atmospheres. So now we have an issue. So Henry's law has enabled us to calculate the acetic acid concentration in a partial pressure. But if we want to compare it to those numbers that we saw before, we need the concentration in milligrams per meter cubed. So what we can do to do this conversion is we can use the ideal gas law. So I'll rearrange to get the moles of acetic acid per volume using this equation right here. And then I can, with moles per liter, I can do some additional calculations to convert that into milligrams per meter cubed. So you see here that we have a concentration of 2,700 milligrams per meter cubed acetic acid in the headspace. That is a lot. So remember, the irritating concentration that we looked up was 25 milligrams per meter cubed. So we are several orders of magnitude over that. So if we, if I wanted to open that bottle and take a big whiff, I would not be a happy camper. So we've used this information on the bottle, that's just the percent acetic acid and Henry's law, to determine that we would definitely not want to open up this bottle and make a big inhale. But I mean, vinegar is something that we use all the time, right? So what if I opened up that bottle in a room and the air in the headspace mixed in the whole room? Would it be irritating to the people in the room? Would they even be able to smell it? We can make some quick mass balance calculations to give us a decent idea. But first, we've got to make some assumptions. So to make this problem one that we can pretty quickly solve, let's assume that the air in the room is completely mixed. I'll also assume that there's no flow into or out of this room. It's a closed room. And I'm also going to assume that no additional acetic acid is added to the air. So we're just going to say that whatever acetic acid was in this headspace right here just mixes with the entire room, and we don't get more vinegar or acetic acid vaporizing from the liquid. So if we look at our law of conservation of mass, we can say, given these assumptions, that the mass in the headspace is going to end up equaling the mass in the room. And then what we want to do is figure out what those masses are. So we can do this by multiplying the concentration of acetic acid in the headspace by the volume, and then the concentration in the room by the volume of the room. So let's just say our headspace is 750 mils, and we already calculated the concentration in that headspace using Henry's law, and we found it to be 2,700 milligrams per meter cubed. And let's assume that our room is 300 square meters. So we can rearrange for the concentration in the room, and we find that that concentration is 0.007 milligrams per meter cubed. So we saw before that our low odor threshold, which is the lowest concentration most people can smell, is 2.5 milligrams per meter cubed. So our calculations indicate that no one in the room is going to be able to smell the vinegar. So if you have vinegar in your house, you can go do this experiment. If you do, pause the video, go open a bottle of vinegar. It doesn't have to be distilled white. It could be apple cider, or whatever you have. And then just make some observations. So you may have confirmed our findings. If you were close to the opening of the bottle, you may have actually smelled the vinegar, despite what our model found. This is because vinegar will diffuse out of the bottle into the room. Therefore, our assumption that the room is completely mixed isn't completely accurate. You may be able to smell the vinegar if you're close to the bottle because the concentration of acetic acid in the air is going to be higher closer to the bottle. However, you hopefully can see how making the completely mixed assumption, although not perfect, allows us to quickly solve this problem. So, like they say, our model isn't perfect, but it is useful. So we can say that generally people in the room will not be able to smell the acetic acid, and we know that there's no real danger unless you're taking some big whiffs straight out of the bottle. So this concludes my introduction of Henry's Law. You will use Henry's Law whenever you have the concentration of substance in a liquid and you need to find that concentration of that same substance in the air at equilibrium, or vice versa. If you ever see both liquid and vapor phases in a problem, you should consider Henry's Law as one way you might find the solution. So remember that Henry's Law does assume chemical equilibrium. So it is best when used when liquid and vapor phases have been in contact with one another for some time. If you are considering the mass balance problem-solving framework that we've been working on, Henry's Law would fall under the category of physical properties and laws when you're trying to find equations for each of your unknown variables. So now that you've seen this video, you should be able to use Henry's Law to calculate equilibrium liquid and vapor concentrations, and you should be able to integrate the use of Henry's Law into our pre-existing problem-solving framework.